Hello, greetings everyone. Thank you for joining our second pre-conference webinar for the 15th Asia Pacific Conference on Combustion, or in short, ASPEC. Do allow me to first introduce to you about the ASPEC. It is a regional combustion conference sponsored by the Combustion Institute. The first ASPEC was held in Osaka, Japan in 1997. And the initial conference set the stage for all the subsequent meetings, emphasizing the importance of regional collaborations and the exchange of scientific knowledge in combustion science and technology. So we have the ASPEC held every 2 years, and its locations rotate among different Combustion Institute sessions in the Asia Pacific regions. Previous host sessions have included China, Japan, Korea, Taiwan, India, Saudi Arabia, and Australia. In 2025, the ASPEC has some new changes. For once, it is being hosted by the Singapore sections of the Combustion Institute, which is the latest sections that has been approved by the Combustion Institute. Second, there is also an exciting news about the possibilities to transfer an ASPEC paper publications into the proceedings of the Combustion Institute for the odd year. Right, so on that note, do take note that our submissions has actually opened since September 15th, and we'll be taking in submissions till December 1st this year. Now, so for ASPEC 2025, it will continue to be a vital forum for the combustion research community in the Asia Pacific regions. And we have this theme to build, excuse me, to build zero carbon and sustainable futures for ASPEC 2025, which is a very good connections to our pre-conference webinar today, which I have proudly named as the Achieving Sustainabilities with Intelligence for today's focus of the webinar. And I'm proud of this name because I came up with it with the intentions to do a pun, because intelligence, of course, I'm hinting at a very relatable techniques these days, which is artificial intelligence. And that will be the main focus of today's talk on how our speakers will be sharing using AI in their respective area of the research in terms of energy as well as combustion. And of course, relatable because there was this recent news that came out in terms of the Nobel Prize in Physics 2024 about how Hopfield and Hinton has developed the foundations for AI. And I believe this has led us to today how we can actually use AI in terms of, again, combustions and energy conservations. Right, so we have two speakers for today, very close to heart. I would like to just briefly introduce, we have Harpreet Sethi from NVIDIA, Harpreet, and who will be the leading speaker for today, and then followed by Matthias Ihme from Stanford University. Brief introductions on Harpreet. So Harpreet is a solutions architect for energy at NVIDIA. His work focuses on building artificial intelligence factories and digital twins for scientific applications using generative AI and physics for machine learning. Harpreet has received his PhD in geophysics from Colorado School of Mines and obtained an integrated master's and bachelor's degree in the same discipline from India Institutes of Technology, Rocky. So Harpreet today, he will be highlighting a topic which is predicting carbon dioxide, CO2 plume migrations in carbon storage projects using graph neural networks. Harpreet, over to you.
Yeah, thanks for the introduction. So I'll just start sharing my screen. You guys can see my screen, right?
Yes, we can.
Cool. So thanks everyone, first of all, for joining this webinar. And so as my title says, I'm going to talk about CO2 plume migration using one particular AI model called graph neural networks. So, but before I went deeper into it, so I briefly want to touch on some other things. So basically, this work was done using a package called NVIDIA Modulus. So at NVIDIA, we developed this package particularly for like AI for physics applications. So these are a collection of AI models that are particularly useful for developing physics-based surrogates. And also, and I will also talk about like the reason why we choose this particular model called graph neural networks and how it can be applied for, in general, any kind of CFD problem. So this webinar is particularly focused on combustion. So you can imagine you can also use these particular type of models also for combustion problems or any kind of CFD simulations. So before I start my presentation, so this is just a disclaimer, and this work was particularly done in collaboration with the NETL. So NETL is a National Energy Technology Laboratory based in US. And so these are some of our collaborators. And this project was funded by Department of Energy US. And NETL was the main organization who led this work. Basically, at NVIDIA, we were just their research advisor. So NVIDIA in general doesn't like to do the research on their own. So we like to partner with different research organizations and research institutes and enable their research. So that's how in general we work at NVIDIA. And if you are interested in hearing more about this or you want to collaborate us, feel free to reach out to me after this presentation. So let me first start with this package called NVIDIA Modulus and what it can do for you. It's a package focused for building physics-based ML models. And it's an open source package, as I mentioned. So anybody can basically develop their solutions on top of it, and it's free to use. And so the reason why we built this was because a lot of the research codes that you find online, it's not easy to reproduce like all the results sometimes, and it takes a lot of time. So basically, it's a well-maintained package. We have a lot of like samples. Basically, you can take those samples and use it as a starting point to develop your own solutions. And obviously, this package supports our NVIDIA GPUs, and you can basically build like industrial scale solutions. So a lot of the research code doesn't scale really well. They are mostly single GPU solutions. So this package basically makes sure you have these multi-node and multi-GPU parallelism. You just get this like out of the box. And it also provides you a lot of like utilities basically to add your own physics. So basically, in this box, you say it has the ability to satisfy mathematical relationships and any kind of PDEs. So you have this freedom, basically, whether you want to rely on data, whether you want to rely on physics, or you want to rely on hybrid trainings. So we have a collection of different models available, and with each model, you can basically choose the style of training that you want to use. And this package is available as a part of we call as the NVAI license. So and also this package is open source. And a lot of different research organizations and also like people in the industry have used this package to develop different solutions. So in the energy industry, people have used it for like wave simulation, CCS problem, and here you see some like wind farm simulations and heat boiler plants. And there's a lot of work we did in the climate and weather space. And this have been also used in our own internal research for designing like chips and heat sink designs and medical healthcare, like blood flow simulation, MRI imaging, and also CFD simulations around cars. So there are many different fields. This package has been already adopted by people. So there are a lot of examples available in this package you can use as a starting point. And I will point the link out at the end with the GitHub. So, and this slide basically goes a little bit deeper into what type of models are available, but it keeps evolving. So we have like more and more models available, like pretty much after like every release, and every release is roughly like 3 months. And so, as I mentioned earlier, that you have this freedom to basically choose which way of training you want to basically choose for your building your surrogate models. So you have this on one spectrum, you have fully physics-driven basically models called physics-informed neural networks, and on the data-driven side, and one of the model I'm going to talk about is graph neural networks. So it's more on the data-driven side, but we have other models available: neural operators, diffusion models, physics-informed graph neural networks, and physics-informed neural operators, and many more. And I think we are also planning to release maybe one or two like foundation models for the simulation purpose. So it's a evolving package, and we are like there's a lot of big team behind it. So anybody, but it's still open source, so anybody can use it to develop your own, accelerate your own research. So now coming into this one particular model called graph neural networks. Uh, so basically, I'm going to start with what are these graph neural networks first. So you might be familiar with like normal neural networks. Uh, Basically, graph neural networks is just like a way where we use a normal neural network and adapt it to on a graph type object. And on the picture on the right hand side, you see how a graph looks like. So a graph is composed of nodes and edges. And so you can see these different colors nodes, and the lines connecting these nodes are edges. And there are many things that can be represented as graphs, like social media networks. So the interaction between users can basically model as a graph. So molecular structure can be represented as a graph. But in this example, we will only are interested in meshes, how we can view a mesh as a computational mesh as a graph, and how we basically we can train a AI-based surrogate model on top of this computational graph. And in general, when we talk about graph neural networks, we are interested in three tasks. So one is called node level prediction tasks. So node level prediction tasks means if you define any quantities on the nodes. So in this case, basically, we will be interested in predicting pressure and particle velocity at our mesh points. So this is equivalent to like a node level prediction task. So that's what I will be talking about later on. And the second task is like edge level prediction. So basically, we are interested in predicting the missing links, or how the position between two nodes are changing. Like a good example would be like predicting molecular forces between atoms as their position changes, or maybe, or your mesh is changing over time. So you're interested in how the position of nodes are changing. So that will be like the edge level prediction task. And third is the graph level or global level prediction task. So we are interested in one global property of a graph. So one good example would be, given a molecular structure, what is the basically the smell of the molecule or something. So like a global level prediction is basically you're predicting one global property of a graph. So these are the three tasks that people normally are interested in when they are using graph neural networks. So now, as I mentioned, that you can basically use these graph neural networks for any type of CFD problems, even in your combustion. Uh, so this is a very one simple problem. So this is a flow path through a cylinder. And in this case, you have a fluid flowing from the left-hand side. So this is the inlet region, and it is exiting from the right-hand side. And so we are interested in training an AI-based surrogate model, which can handle basically, which can predict the changes, how the fluid will interact with these different size of the cylinder. So you can see the size of the cylinder and the position of the cylinder is changing. So it means the mesh is also changing. So we want to develop an AI-based surrogate model which can basically adapt to these changes during the inference time. Um, so how these graph neural networks can be used to basically develop these surrogates for mesh-based simulation. So the first step is um, you have this information available from your numerical simulations. So as I mentioned earlier, this is a data-driven approach. So you need to generate some sort of simulations for different type of meshes. So assuming that you have some simulations available, you have this pressure and particle velocity information available. And so in this case, we also have another feature called node type. A node type is like a one hot encoding vector. Basically, it tells you where actually the node lies, whether it's close to the inflow region, outflow region, wall region, or interior region. So basically, in this case, we have four like classes. So if it's close to the wall, so I'm gonna um, put my node type vector as 1000. So depending on which region it is, so I'm just gonna basically change the 0 to 1 to that region. And other information that I have available from your numerical simulation is basically the position vector. So basically you have this idea of where each node is located. And so we have this positional information. And the first step is basically how do you encode this information on a node or on an edge of a graph. So in this case, we encode pressure, velocity, and node type as a node feature, and the other positional information on the edge feature. So I won't be able to go into detail exactly how graph neural network works, but maybe I'll mention some important points. So to create this node embedding and edge embedding, so this NI and EI represent node and edge embedding. So you can basically imagine there is a neural network sitting on at each node and each edge. So basically it takes these input properties and it converts them to embedding. And so you have this node embeddings and edge embeddings. So that is the first step. We call this step as the encoding step, that you encode the information that you have available from a numerical simulation on a graph. So that is the first step. And once you have these node and edge embeddings, so the second step is called processing. That how do you update the information now? So to update the node embeddings, so basically you look for which edges are connected to this node. So you take the information on the edge, you combine them with the initial information present at that node. So somehow you can imagine you take this edge information and the node embedding, and you can say you pass it through another neural network, and that's basically how you update the information. Like that's how you update the node embeddings. So you take the information from the neighboring edges and you update it. And similarly, to update the edge embeddings, so you see which nodes are connected to that edge. So in this case, the EI is connected to NI and NI plus 1. So you take the information from these two nodes and combine with the initial edge embedding, and you pass it through another neural network to update the edge embedding. So we call this uh, a step called processing, or it's called like message passing also. Basically, the nodes and edge basically pass messages with each other. So the messages are these embeddings. So this is the second process. So that's how you update basically nodes and edges. And the third last step is the decoding process. So once you have updated these node and edge embeddings, so you need to convert back into your the original space. So in this case, we were interested in predicting the pressure and the particle velocity only. So we are using one decoder basically to convert this node embeddings back to pressure and velocity. So in this case, we are not using the decoder on the edges because our mesh is static. So, but in some cases, you also want to predict like, as I mentioned, like dynamic molecular simulation is one example where you're also interested in predicting what kind of forces. And in those cases, you would also use like a edge decoder. And also you can maybe use a node decoder as well. So, but in this case, our mesh was static, so we only use a node decoder. So just to summarize for how graph neural network works, so the first step was to encode features. The second was to how do you basically update this um, features based on the neighboring points and how they pass messages with each other. And the last step is the decoding. So once you update these nodes and edges, so you need to predict basically the next time step prediction. And these graph neural networks traditionally or we call in literature, you call them as a mesh graph net because you adapted it on the meshes. These are autoregressive methods. Basically, you predict in a one-time step fashion. So, um, and yeah, so in nutshell, this is how a graph neural network can be adapted for a mesh-based simulation. And these are some of the reasons listed that why do you want to particularly use graph neural networks to develop your AI-based surrogates. So one of the main reason is it can handle your unstructured grids and very complex meshes. And in this case, basically you are trying to adapt basically to unseen meshes, and so you can handle your deformities, cavities, and fall. In CCS, we are interested in like faults and fractures, but these are really suitable for very complex meshes. And you can generalize over meshes, you can generalize over different material properties, different boundary conditions, and also these are also like very like efficient methods. So these are some of the reason why we choose this graph neural networks over like other ML models. And the main reason was the ability to handle these unstructured meshes and deformed meshes. So now coming to the CCS part of the presentation, that why it is important for NVIDIA and Nettle. And the reason is because of the climate for task force goals. So these are some of the goals listed by the US government that by in 2030, we want to reduce our greenhouse gas emissions almost to like 50 to 52% in 2005 from the levels in 2005. And we want to ultimately be a pollution, like a zero carbon by 2035. And so these are some of these like these goals toward basically to decarbonize, and that is the reason we started looking into the basically how AI can be used for the CCS applications, and how we can basically monitor our reservoirs and keep and keep store the CO2 safely in our reservoirs. And these are more details on the actual site that we used to basically to train our AI-based surrogate models for the CCS. So this site is actually based in Illinois State in the US. And this is actually like a real site where people have injected almost like 1 million metric tons of CO2, and the actual depth of the reservoir where we are storing the CO2 is roughly like 7,000 to 8,000 feet deep. And we normally store this in a like a thick and porous sandstone. Because a lot of it has a lot of like storage available, and there's a cap rock on the top of the sandstone, basically, which ensures that none of the CO2 can escape, and that normally is like very less permeable like stone. So this is a very well tested site where a lot of CO2 has been injected like with no safety issues. And so these also have some wells available to basically to monitor and to collect the data. So we have a lot of data available from this site, and that is one of the reasons we chose this basically to see if we can develop an AI-based surrogate for this site or not. And these are some numerical details on the type of grid that is involved. So it's not like a regular grid. So you can see it's a tartan grid. This is like a deformed type of grid, but eventually we want to basically able to handle like faults and cracks and this type of grids. So that was the reason we chose for the graph neural networks. And the table on the left shows you some of the properties that are available. So basically, we encode these properties mostly on the nodes, and the other distance information from like the well, how far this point is located from the well location, and also whether this node in the graph is our source, which is basically the well area. So we have this basically the freedom to choose uh, yeah, like each node separately. So that is one of the another advantage of the graph neural networks. And we can also basically generalize over different sources with graph neural networks, but we haven't tested it out for this particular example. And this gave you like a rough idea of the input material properties, that how strongly they vary over space. So this shows you the average permeability and average porosity. And and the graph here basically it shows how the CO2 was injected. So the CO2 was injected mostly for the first 3 years, and there's a 1 year post-injection periods. And the number of model that was used to train this AI-based surrogate is only 100 samples. So this model is only trained on like very few samples. And these are some of the results from these graph neural network based predictions. So on the left-hand side, we have like a numerical solution from the numerical solver, but based on this models from the real data. And in the middle, you can see the prediction from a graph neural network. And on the right-hand side, you see the difference between these predictions. And basically, we have like one well location where we actually were able to inject the things from the real data and basically do like a hybrid training, like a physics plus a data-driven training. So in this slide, basically it shows you like how accurate our graph neural network was in comparison to the numerical solver. So in this case, we only tried like a vanilla graph neural network. So these are the results from the beginning of maybe this year or end of the last year. So this was one of the first experiments where we actually graph neural networks was tried on like a real data set, and we only achieved an accuracy of 93%. But now we have developed like more advanced models called like graph transformers, which is also available in Modulus. And you can also use it for other applications, which are giving much better accuracy, like 98 to 99% accuracy almost. And on this slide, you also see these two lines, like the red and blue lines. So in previous slide, I mentioned that these graph neural networks or mesh graph nets are single time step prediction or autoregressive methods. But we also modified, instead of predicting one time step, we try to predict like 4 or 5 time steps at the same time. So we saw some improvements. So the red line actually have less error slightly than the blue line. So predicting multiple time steps at the same time actually were giving better results. So yeah. But we are actually working on this and improving this model, as I mentioned, and we have developed something called graph transformer model, and we will share the results after getting approvals from the DOE, maybe next GTC or some other relevant conference. So basically, to conclude my presentation, I discussed about the NVIDIA Modulus package, so which you can use to build your own physics-based like AI surrogate models. So it offers you both like physics-based or completely data-driven and hybrid like training utilities. So you have this freedom to choose. And I only discuss in this slide one particular model called graph neural networks and how it can be used for CFD simulations in general. And later on, I showed one example on CCS simulation. And this graph neural networks can offers you different type of generalizations like over meshes, boundary conditions, and these are really suitable for like deformed meshes or very complex meshes in general. And basically, and for the results from the later models will be shared like later, as I said. So with that, I conclude my presentation and feel free to post questions in chat. I think the QA session is after the both talks, so I'll be happy to answer the questions in the chat or later.
All right, thanks, Harpreet. That's a very interesting talk on CCS simulations and using NVIDIA Modulus in particular. Like Harpreet has done the job for me. Thank you very much. I did forget to mention earlier, please post your questions with the Q&A widget. It is right at the bottom, so refrain from using the chat for the questions so we can actually keep track of all your questions and answer them after our next speaker. And I would like to introduce our second speaker, Professor Matthias Ihme. Matthias is a professor in the Department of Mechanical Engineering at Stanford University, as well as the Department of Photon Science at SLAC National Accelerator Laboratory. Matthias' research interests are broadly on the computational modeling of reacting flows, development of numerical methods, and the investigations of advanced energy conversions concepts and molecular processes. He has numerous awards. So I will just name the more recent one. He is the Hiroshi Zuji Early Career Research Award in 2017, as well as the Bezel Award of Alessandro von Humboldt Foundation, in 2021. And today, Matthias will be sharing with us about his work on AI for energy and combustions. Over to you, Matthias.
Thank you, Eddie. Really exciting to be part of this adventure. Oh, sorry, let me stop sharing. Let me just share my slide deck. All right. All right, welcome everyone to this exciting meeting, and I'm really excited to have the opportunity to talk to everyone. I hope everybody can hear and see me. What I like to present is a couple of snapshots on the general topic of machine learning or AI for combustion and energy. And I want to start out by just reminding us that in our community, more broadly, energy conversion, sustainable energy utilization, we have actually quite a bit of knowledge, fundamental knowledge in the governing physics. And this is kind of reflected here on this slide deck, where I'm essentially showing examples of governing equations that are used to describe complex fluid flows. The challenge, of course, is despite this very fundamental knowledge, the challenges arises just from its practical implications. And if you're looking to one of these gas turbine combustors here, you're essentially observing that there are different physical processes that come at play. In addition to this, if you're considering turbulent reacting flows, we have to deal with multiple length scales that go all the way from the molecular scales to the system level scales, and covering this with conventional CFD simulations introduces a challenge. Apart from this, if you're looking to this equations, which are essentially some filtered form of the equations, you are observing that there are a number of terms appearing that are essentially just a consequence of our averaging procedure. So this is typically referred to as subgrid scale terms that require modeling. So based on all of these physical processes, we can really think about is that the scales, unclosed terms, and the multiphysics constitute a number of challenges for which we have some understanding, but we really believe that data-driven methods can help us to make a leap forward to tackle some of these processes. And what I'd like to show you is, in this few slides that I have here, is some approaches for dealing with some of these challenges. And one of them is, of course, that we have an extensive set of data available. This is shown here by an extensive set of thermodynamic properties that I think many of you have been using for your thermodynamic analysis, for your combustion simulations. This includes phase diagrams, this includes thermophysical properties for heat capacity, diffusivity, as well as reaction mechanisms shown here at the bottom right. So based on this, as we as a combustion community or an energy conversion community, we are relying already extensively on data that have been seemingly integrated in our workflow. Apart from this, what we're also recognizing is that there is more and more sensors and diagnostics coming online that is useful for diagnosing combustion performance, and this adds some additional opportunities for us to take advantage of this. And lastly, of course, our extensive simulation database from experiments as well as simulations that can be utilized to extract additional knowledge and perhaps tackle some of the challenges that I mentioned before in terms of scale separations, multiphysics, and unclosed source terms. Right. So by and large, the question then is how can we combine our existing knowledge and available data in order to make a leap forward. Right? And what I'd like to do here is to kind of show you a couple of snapshots on different aspects. The first one is essentially a data and open source community-driven approach, where we're really thinking about this data that is available, typically dispersed within our community, should be somewhat combined so that we have access to this data for numerous data-driven methods. depending on the time, I want to briefly touch on the use of this large data sets for extracting physical knowledge. And then I want to branch over on giving you some ideas on how we can combine physical understanding and data-driven methods in order to tackle problems for which we have very limited capabilities to comprehensively investigate those. All right, so let me get started with the first step. This is opportunities for data-driven methods. And what I want to show you here is just an example from the past literature on one large data set, which I believe was kind of an exceptionally impactful contribution to the community. And this is essentially a set of data or images that has been used in order to calibrate and benchmark different machine learning models. So what you're seeing here is large data is helpful for us as a community to advance the state of the art in the machine learning techniques. And this is nicely illustrated here. If you're looking to this bluish line, you're essentially seeing the growth in the model accuracies. And this has been enabled by 2, perhaps 3 effects. One of them is available data. The second one is a community that brings together the data and builds on this knowledge. And the third one is compute power and advanced machine learning models. Right? So what we like to see is to take some of these concepts and apply this in our combustion community. And one of the data sets that is perhaps most relevant is this Johns Hopkins database. This is a turbulent database and high fidelity set of DNS data. And what you're finding is that this database was specifically designed for scientific discovery, but perhaps not so useful for machine learning tasks. And the reason for this is that this data is not particularly diverse. So in total, we have about 9 unique configurations. If you're comparing this with this 15 million individual snapshots and about 1,000 diverse objects, it is a substantially scale separation, right? In addition to this, if you're thinking about DNS data, detailed numerical simulation data, and these are typically 3-dimensional, unsteady, and very large. So if you're contrasting the data size, you're finding that despite this few configurations, the data set is several orders of magnitude larger, right? So it makes this really challenging to translate some of these concepts from 2 dimensions to 3 dimensions and adapt this to our fluids and combustion community. So with this, there's clearly a gap, and what I like to show you is an effort and community-driven effort. This is reflected in this notion of BLASTNet, where we are trying to bring together high-fidelity data in order to centralize them and make them accessible for the broader community. And we're referring to this as a BLASTNet database. There's an acronym which essentially alludes to the idea of making large DNS data publicly available. Idea is the following. Step number 1 consists essentially of the generation of the data. And I think many of you perhaps have generated high fidelity simulations that are published. And the challenge there is that they're perhaps sitting locally on a server behind a firewall, but are not accessible to the community. So what we are proposing here is essentially to use open source data storage systems. One of the examples is Kaggle, where we essentially have data storage available, and we are essentially leveraging this open resources to port this DNS data in a user accessible and in a generic data format to this database. BLASTNet then, in essence, is in curation systems where it provides essentially metadata interfaces to this data set so that you as a community can utilize this for various machine learning tasks. And by this, we have essentially a pathway forward in order to enable broad access of high fidelity data for machine learning tasks, for data-driven tasks, and for various analysis tasks. And I think this is certainly an exciting prospect. Currently, BLASTNet is rather diverse. The latest version consists of about 35 unique configurations. So you're seeing we are not quite there at this ambitious goal of having 1,000 unique objectives, but we are clearly moving in this directions. The current database is about 5 terabytes of data, and it has a wide range of different configurations that starts out from homogeneous isotopic turbulence to various combustion configurations, all the way to ammonia and hydrogen fuel combustion applications, right? What I think is perhaps most notable is that if you are contributing to this database in different forms, either by sharing data, by providing scripts, or by providing machine learning models, you will essentially become a co-author and obtain corresponding attributes. And by this, we hope that we can grow our community more broadly and essentially move towards a general data set that is accessible for the entire combustion community. Right. So what I want to show you is in a couple of slides, just a couple of ideas on what the utility is of this BlastNet database. And as part of this early task, we essentially started out with a so-called super resolution approach. What you're seeing here on the left-hand side, we essentially used some filtered DNS data. This is essentially a pixelated image. And the task from this is that if you're giving this under-resolved flow field simulations, or in this case, a momentum flow field result, the task was to reconstruct the true solution. And this is typically referred to as a super resolution task, but it's equivalent to a deconvolution approach. What you're finding is that if you're using this BlastNet dataset with one particular subset of data that we refer to as momentum 128, we essentially can filter this data at arbitrary order and obtaining information about the diversity. The diversity is a good indicator on how spread, how this data set is. And this essentially alludes to this idea that if you're developing a machine learning model, it provides you access to general data. And if you have a diverse data set, we're not running into the issue of potential extrapolation errors or hallucinations. So diversity is really helpful, especially if you're thinking about developing machine learning models that are generic, that are applicable to a wide range of operating conditions. And this is where we think that this BlastNet dataset provides quite a bit of value. One example of this is that now that we have this rather diverse data set, we can essentially test different machine learning models. This is illustrated here on this slide. We have our ground truths. This is our reference solutions. We are filtering at different scales. And if you're doing a naive tricubic interpolation, that's kind of a standard approach. We are recovering some of the solution fields. What you can also do is we can train a number of different machine learning models. They have different acronyms, residual and residual dense blocks. We have the enhanced deep residual network and other formulations all the way to a Fourier neural operator. Now we can test the performance of different models, and we can ask questions how different models scale with regard to the number of data that we provide, or how the different machine learning models scale with the size of the systems or with the number of degrees of freedoms. And I think that's really an exciting opportunity for us to look to asymptotic limits in different machine learning techniques, right? Again, illustrated here, just one snapshot of this. We're picking one particular model as our DB model, where we're increasing the number of parameters or model weights all the way from 500,000 free parameters to 50 million. So we are essentially changing this by 3 orders of magnitude. And by this, we can test different performance of the model. And what you're clearly seeing is that there is a tendency of approaching an asymptotic limit. And that's what we're interested in exploring with this large data set, right? Just as a side note, if you have a singular data set, you cannot test this because you're ultimately running into the issue of overfitting your machine learning model, right? So the results that we're getting is quite exciting because you are now able to observe trends, asymptotic limits, and this is essentially in performance metrics where we can now assess asymptotic performances of different models and really nudge towards this idea of generating foundational machine learning models for the combustion. Clearly, what you're seeing here is there are certain models better, and this is, again, and really good indications if we are intending to use one of the models for different combustion applications or turbulent flow field applications, as opposed to other models which perhaps have a lower performance. Okay. So with this, let me briefly summarize here. So BlastNet is a community-driven effort in order to bring data from diverse data sources, most notable from high-fidelity DNS simulations, in a central repository where we as a community can use this for different machine learning tasks. There is clearly opportunities to grow this data set in different directions. Currently, it's mostly focusing on turbulent fluid flows and turbulent reacting flows, but we could equally envision that this expands to experimental data as well as biofluidic flows, environmental flows, and related applications. Right. So I think this is a really exciting perspective, and I encourage everyone to consider contributing to this database. Right. With this, the remaining few minutes, I want to switch gears here and show you another application. So we're going all to the extremes. First example essentially talks about available data. What I want to do here in the remaining few minutes is to give you an idea where we essentially have to think about a different approach. This really has to do with sparse experimental observations and the question, how can we augment sparse computational simulations in order to forecast dynamical systems. And an example that I want to show you here comes from the rocket combustion community. And there the challenge has to do with the ignition of different propulsion systems. By the way, that's not only relevant for rockets, but in particular, it's a challenging task because rockets are requiring a high degree of accuracy and reliability so that any of the space missions are guaranteed to succeed. One of these techniques is a laser ignition system. So you're looking right inside a combustor and rocket combustor here at the upper right. And this is typically facilitated by a laser spark. And what you want to guarantee is that each time we're firing this laser, that we have a successful ignition. You can imagine that if you're igniting in regions where you have only fuel or oxidizer, ignition is very unsuccessful. And so what we're trying to find is predictive methods on how we can position this laser, this ignition source, so that the ignition is always 100% guaranteed. Okay. So it turns out that if you're doing this kind of experiments, it is an extremely challenging combustion environment, and you typically have only access to a few experimental data. So in our case, these are on the order of a few hundred unique experiments. But at the same time, if you're thinking about performing high fidelity simulations, again, we are limited by the number of ensembles that we can access, right? So we kind of have a limited data set and we have limited computational capabilities. And then the question is, how can we marry both in order to get an ignition map with minimal availability of data, right? So this is really extrapolations in the sparse data limit. And what I want to show you here is an interesting attempt to combine this so that we have predictive accuracy. Right, so what you're finding here is, as I said, ignition is limited by the turbulent mixing, by the unsteadiness and the stochasticity of the combustion process. And what we would like to do is we like to combine in single or in sparse high fidelity simulations. And this is shown here on the right-hand side. This is one CFD snapshot of cold flow simulations. This essentially provides us the fluid dynamics and the flow field behavior. In addition to this, we have sparse experimental data. You're seeing here essentially the rocket combustor, and we're injecting oxygen, and the shear layer is the methane injection. And each one of the symbols is one unique experimental data set. So you're seeing already, this is clearly in sparse data set. And we want to combine this in such a way that we can predict the entire ignition map for this case. Right, so in total, we have about 150 ignition tests, and we have one three-dimensional LES calculation. Right. So with this, the question that we have is, can I use this sparse experimental data set and this limited CFD simulations to predict the ignition map? And the idea that we are doing is we're essentially analyzing the data from a number of those simulation experimental results to extract this ignition kernel shown here in this red curve. And then we want to combine this with our CFD simulations to extract some of the characteristic flow field behavior, most notable the velocity field and the scalar mixing quantity, which are essentially the most relevant quantities to predict the scalar mixing and the flow field behavior. In the second case, we're combining this in a two-zone model, and it is essentially a hierarchical modeling approach where we're combining both a classical machine learning technique with a physical model. This is illustrated here. So the first one is a classical UNet, which essentially allows us to predict the geometry of a particular ignition kernel, right? So we are essentially taking this initial state, I hope you can see this here, this red curve, and trying to predict the next instance after the evolution of this ignition kernel. What this machine learning technique is not able to do is to provide the dynamics So we're not able to extract the convective behavior of these ignition kernels or the mixing. And for this, we're using essentially a physical model. This is here expressed in the form of a so-called stochastic differential equation. So what we're doing is we're essentially advancing this ignition kernel here expressed in terms of the center of mass by some convective velocity and some stochastic behavior. And those quantities essentially are calibrated from our physical closure model. Right. So with this, we are separating the physics in one where we know that machine learning models are really great, and this is essentially identifying features. And the second one is leveraging our knowledge about the physical behavior, and this essentially relates to the behavior of the fluid dynamics. So with this, I want to show you two results here. You're looking here in three different events. The red kernel is the machine learning model. The Schlieren image is the experimental data. We are seeing at the bottom an unsuccessful or a failed ignition. The figure in the middle is an indirect ignition, where we're essentially seeing some interesting interactions of the ignition kernel with the incoming combustion or fluid flow. And the last result is the direct ignitions. And what you're clearly seeing is that there is reasonable agreement between the machine learning model shown in red and our experimental data for this basic set or for this three experimental data. The real question that we're asking is, can we also apply this to our sample simulations and essentially extrapolate within our combustor system? And this is nicely illustrated here on this slide deck, where we're showing on the left-hand side the machine learning model, this SDE-ML model, where we are identifying trajectories. And this compares very well with experimental data. If you're moving on to quantify this, you're finding that our model is within 5 to 10% accurate in predicting the ignition delay time, or in the, more specifically, the time to ignition. So overall, the model captures all of the behavior. The real interesting question is that we want to also populate ignition maps. Just to remind you, each one of the symbols is an experimental data point. And of course, our machine learning model is able to capture this because we trained for this set, considering the training and test set. The really interesting question here is to generate populations, our samples, large-scale samples. And this is illustrated here, where we show on the left-hand side essentially an entire ignition map. And to illustrate the merit of our stochastic differential equation, I'm showing here on the right-hand side essentially the effect of turning off our advection model expressed in this SDE formulations. And you're clearly seeing that the ignition boundary is very discrete, again, in consequence of neglecting some of the turbulent mixing, right? Another question that is interesting to ask is, how does this model perform if we're extrapolating? And many of you know that machine learning models tend to hallucinate, meaning that for conditions outside the distributions, that the model introduces generates results which reduce credibility. And we're testing this here as well. And what you're finding is that the model is performing reasonably well, at least from a physical perspective, that if we are increasing the velocity at the inlet by a factor of 2, so considering higher mass flow rates, we're clearly finding that the ignition probability reduces, it becomes more compact, and we're also seeing some notion of liftoff. And you can rationalize this by essentially thinking about an ignition delay time and convective time. Faster velocity reduces the convective time scales, and by this, we're reducing the area of the ignition probability. So overall, I think the model captures some of the key features that we would expect by our intuition, and I hope I conveyed the importance of introducing some physical knowledge so that we are accounting for some of the turbulent mixing. So with this, let me put here the summary, and so what we or let me show you the summary. So what we presented here is a modeling approach where we're combining physical knowledge and machine learning techniques in the sparse data limit in order to predict some stochastic ignition events that are particularly for a number of combustion problems. With this, let me summarize here. So I try to give you a little bit of overview about trends in this direction that I think is quite exciting. Most important is the use of data and making this data available to the broader community so that we can really advance this field and leverage some of this experience that we have observed in other fields. And then I showed you one interesting example on how we can combine both experiments and simulations in order to predict stochastic ignition events in the sparse data limit. And with this, let me finish here and thank you for your attention. Thanks.
Right, thanks, Matthias. If I can invite Harpreet to maybe return with the camera. Thank you very much. Thank you both for the sharing. Like I say, the theme today for the webinar is nicely named as Achieving Sustainability with Intelligence. I can hope that we definitely will reach our goal of building a zero carbon and sustainable future. And the intelligence part, I think we have convinced most of the audience today that AI definitely has its place in our research for combustions and energy science. And also, of course, not forgetting the domain experts, a lot of intelligence from our speakers here showing how the domain expertise, knowing some of this prior knowledge is equally important. Right, so we will have let me take a look, about 10 minutes for our Q&A. Do allow me to have the sessions overrun just slightly by 5 minutes. In my world of meeting overrunning 5 minutes is considered as on time. And I think everybody can agree with that. Right. So for Q&A, like mentioned, so you can keep the questions coming. You can send it in through our Q&A widget. So far, there actually has been 2 questions. Maybe I'll just read it out, and Harpreet has kindly answered them through the text as well. So just for sharing. The first one is in terms of, I believe should be for NVIDIA Modulus interface. So it is PyTorch. Okay, Modulus is based on PyTorch. Second is a whole series of questions. First is, can we use the NVIDIA Modulus models for acoustic analysis in combustions? And the answer is yes, it can. Well, it's a short answer. And the mesh support it offers, what type of mesh support does Modulus offers, like conformal and non-conformal and type? The answer is it supports both conformal and non-conformal meshes, excuse me, and PyTorch DJL libraries that can help to convert the meshes to computational graph. Third question is how bad mesh we can use and yet we'll get accurate solutions as good as perfect mesh. I think I'm paraphrasing a little bit here. So normally we will use the subsample meshes to train the graph neural network models. So we don't need a full resolution mesh for training to maintain the computational cost, and then we can interference on full resolution mesh later. Harpreet, do feel free to chime in at any point if I'm not answering them as what you intended. In terms of Modulus, so user friendliness of the post-processing tools in general, or any limitations. So there are utilities from Modulus for normalizations, and NVIDIA also have other packages for visualizations as well. And finally, Modulus, is it possible to use for new technology like battery or fuel cell analysis? Yes, we can. Okay,
Yeah.
so mostly of the questions. Harpreet, anything to add on, please?
Yeah, I think I just want to add maybe one thing. So Modulus doesn't limit you guys in terms of what type of things you can handle or what type of physics you can handle. I think a lot of the things that Matthias also showed in his presentation, like Fourier neural operator based methods. So they also came from NVIDIA. So we have all these different models available for like super resolution, all these new Gen AI models like diffusion models, GANs and VAEs. And also briefly mentioned, we are also releasing some transformer-based architectures for building foundational models for CFD problems. So we have a collection of different models and Modulus, so feel free and check it out. And you can also add your own constraints. So you can just add maybe light constraints like mass conservation, flux conservation. Sometimes we don't fully rely on the physics, on the exact PDEs because we are not sure. So we can also maybe add some light constraints like I know that flux is going to be conserved and only mass is going to be conserved. So only satisfy while training these ML models. So Modulus offers you all these capabilities. Yeah.
Right. Thanks, Harpreet. Matthias, any comments on it? Otherwise, I
I think,
yeah.
yeah, I
Sorry.
think Harpreet summarized this quite nicely, so I don't have anything to add.
Good. I wouldn't leave you lonely. I do actually have a question on BlastNet, and I think given a time constraint, a low-level question first, because I'm dabbling in the area of also physics-based AI, although I'm not doing the combustion side yet, more for just aerodynamic simulations. But I think we are touching on a topic that data is, of course, very important for the training. So I therefore appreciate the call for having all this data going into BlastNet, but I wonder, like, are we concerned about also the data quality besides the amount of it? And so do you are you controlling some of this if everybody starts submitting their data to you?
Yeah, so that's a really good question. So there are two answers to this. The first one is, well, data quality plays a big role, and we're currently trying to gatekeep this by only accepting data which has been peer reviewed. So that means if there's a journal paper associated with the data, that's one pathway for accepting this. The second answer is perhaps a little bit more pragmatic, and what we're learning from other machine learning applications, for instance, this ImageNet, is that there are a number of mislabeled data already available. So that means our machine learning models can actually handle noise to some extent. So we can probably relax some of our constraints on the data quality, but this is a little bit more risky. So we want to take a little bit more action on this and making sure on how much variability we can tolerate in this data set.
All right, thanks. So great, yeah. So Aspect might be a good avenue for you all to have your data peer reviewed, and then we might be able to contribute more to the BlastNet. And other questions I have actually maybe can stir up some discussion between the two of you. Like, so Matthias, is BlastNet right now also looking, or rather, like, let's just say in your research, are you also looking to say, for example, NVIDIA modulars that Harpreet has presented? Because my understanding about modulars is they are quite friendly towards other types of models. I've heard about modulars before that they allow for even other models to be using the modulars as the background platform. Like, so for Matthias, are you also considering to access some of these packages in your research? And maybe Harpreet, you can also correct me if there's things about modulars that might be more proprietary. Yeah.
Yeah, so currently we're using different machine learning libraries, and this is essential for our work. I think what we have done in this BlastNet ecosystem is that we are providing a number of machine learning models to the community. So I think in total there might be 100 different models. They are programmed in different architectures, and some of them are relying on PyTorch, TensorFlow libraries, and related things. So it's definitely in rather diverse software platform that we're using and we're accessing.
Yeah, and maybe one thing I would also like to add is, so we in Modulus, so researchers also contribute their models as well. So as I said, it's an open source model, and actually we are in the process of adding like a data set called DryAwareNet. So I think it's also like a big data set, but it's around like CFD around car geometries. So I think this data set was initially released by like MIT. So now that's also becoming a part of the Modulus, and they also have some ML models, so they can also contribute. So I would also encourage and welcome like Matthias, if he would like to contribute, like even his data sets or broader, to reach out to like a broader community, so people can access their models and maybe reproduce the results. Yeah.
Cool. Actually, we are close to the time to end the sessions, and right now I'm not receiving any further questions from the audience. So seeing that we are all in different time zones, I think Harpreet and Matthias, over your side, you're about to start the day. And for me, it's actually turning 11 p.m.
Maybe,
So, yeah,
maybe
sorry.
I have one question for Matthias before you end. So
Mhm.
yeah, so I think, so with the BlastNet, so is the goal is to build some sort of like a foundation model for these turbulence application at the end? Is that you guys are moving towards?
But that's one of our key motivations. So providing diverse data that essentially enables a pathway towards a foundational model. Yes, absolutely right.
Okay. Well, I think maybe that there is some way we can also, I don't know if you are interested, we can also, there's a potential to collaborate. I think that's also one of the active like area of research. We have worked already quite a bit on the climate foundation models, and
Right.
next we are targeting like CFD foundation models for car type geometries. So I think since we already have a huge amount of data set available, so I think could be interesting area for NVIDIA itself as well.
This would be exciting to continue this. Fantastic, yeah. Yeah, glad to reach out and continue our conversation.
Yeah, so thank you,
Well,
Matthias.
I might do something more for Matthias. So actually in my university, so Nanyang Technological University of Singapore, the basic issues is that we are running into a lot of constraints in terms of hardware, and I believe that it will be the same case for Matthias' group as well. The more that we try to venture into this area, and obviously NVIDIA being the biggest supplier in the most powerful GPU cards, probably that will be something that will be useful for us researchers. Besides collaborating on data set. I think maybe if we can have some access to some of the hardware itself would be a very useful way to collaborate too.
Yeah, I think we do have like programs and research grants for like researchers to apply for, but I think we can chat later that how we can enable you guys. Yeah.
Fantastic.
Yep. Okay. Well, still not having any questions coming in, so I think it will be a good place to end the webinar for today. Thank you very much for both of us once again. And for our audience, do remember that our paper deadline will be, the submission deadline will be the December 1st, 2024. And it has already been opening for submissions. So please go ahead and do attend our conference. Hope to see all of you next year. Thank you very much.
Thank you for organizing this.
Yeah.
Bye.
Thanks, everyone.